Institute. One more time. Good morning, Summer Institute. All right, I'll take that one, even though it sounded pretty half-hearted. So what week is this? What else is it? It's also Shark Week. That's right, Shark Week. So as you're doing your little videotapes and picture challenges, things like that, just remember to put a little shark fin on your project. And then we'll see what it looks like at the end of the week here. So who knows the shark song? Baby shark, doot, 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 baby shark, doot, doot. Come on, come on. Baby shark, doot, 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 baby shark, doot, 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 doot. Mama shark, doot, doot, doot. Come on, I want to hear you guys. I can't believe you guys don't know the shark song. Well, I'm going to have to practice this later this week. So I want to thank everybody for filling out the course evaluations. We're at nearly 100% for that, nearly at 100%. I know the video shorts are still trickling in, as well as some of the other evaluations. I appreciate that and want to encourage you to get those done as soon as possible so that we can evaluate those to improve the last half of the Summer Institute. So thank you very much, and continue to work on that, because don't worry, there will be more assignments before the end of the Summer Institute for you to work on. I'm going to hand the mic over to Surtash, and he's going to do the introduction here today. Thank you very much.
Thanks. Hi, everyone. How are you guys? Good? Great. And I suppose the applause was Natalia, not for me, for introducing her. So we're fortunate today to have another stellar speaker that I think you guys will really enjoy this one. So we have Natalia Bailey today. Natalia is a rocket scientist by training. She's done a lot of work focusing on a variety of aspects of rockets. Most recently, she started this company called Accion Systems. It stands for Action and Ion. The first product of the company has become little ion thrusters that can actually take certain particles, ionize them, and push it out, so that you can take CubeSats in space and you can propel them in different directions or change their orientation and so on. Prior to that, Natalia was a PhD student here at MIT in Paolo Lozano's lab, who I've seen, he's sitting somewhere here. He's right over there. And Natalia has helped kind of this ion thrusters become a reality in the lab, and then took it out and started this company, has done a lot of other things prior to that related to rockets. And I think she's going to talk about her experience today. Thank you so much. Let's give a warm applause to Natalia. Thank you.
Okay. Thank you all for having me. It's always great to be back at MIT. Right now, I feel, with Paulo in the audience, I feel like a grad student, again, being evaluated. But that's okay. So as you just heard, I'm the founder and CEO of Accion Systems, which was named, I'll switch to this slide because it's more beautiful, was named kind of as a concatenation of accelerate and ion, because that's what we do. But actually, unofficially, the real story is that the name came from a Harry Potter spell, the summoning charm, and if you add an N to the end of it, it becomes a reasonable name for a company that accelerates ions. I grew up in Oregon, was always interested in space. I thought a lot about aliens when I was a kid, but my family was very practical and told me you probably couldn't make a career out of that, so I combined that and math and ended up with aerospace engineering, and have been working on that since late high school into college and my master's, and then my PhD was here working on space propulsion. And so that's what we're going to talk about today, kind of a little bit of the space industry and what's been going on there the past 2 decades, a bit about ion engines and space propulsion, and a little bit about starting a company based on your PhD research and how that's been going. All right. And I prefer very much more of like a conversational format, so please feel free to ask questions during this, and we can just be a bit relaxed, and we'll go from there. Since the inception of the space industry, save for Sputnik, which was technically a small satellite, most satellites over the past 50 years had been kind of like this one here. They can weigh, on the order of 1 to 2 tons and cost upwards of $2 billion to build and launch one. So they, for the longest time, for most of the existence of the space industry, had been primarily limited to, entire countries or big governments. Individuals, hobbyists in their garage, college students, and small commercial companies were not able to, put a Kickstarter campaign up for $2 billion and launch a satellite. So they've been primarily the domain of governments and countries. But about 20 years ago, as you guys, I think, have probably been learning about so far this summer, the researchers at Cal Poly and Stanford got together and realized that you could essentially take the components of a cell phone apart and stick them in a shoebox and launch that into orbit and get it to do some useful things like tweet back at you. And what they realized was that Moore's law had taken us to a point, everybody knows what Moore's law is, yes, had taken us to a point that electronics and components had become so capable at such small sizes and low costs that we actually didn't need to launch such large satellites anymore. We could perform some of the same missions. We could perform new missions, with much smaller spacecraft. And those folks I mentioned at those schools developed the CubeSat form factor, which is a standard, kind of a convenient way to standardize the size and various components of a satellite. But you could actually, build a small satellite in any different shape you wanted. So this has basically had the effect of opening up space to many more people on the globe. So you don't have to be a rich country or a government anymore. You can be, we work a lot with the Irvine High School district, actually, and we're building a CubeSat together with them and putting propulsion on it. You can be a high school, you can be someone in your garage building a satellite, you can be a new startup company. It's basically this realization and Moore's law, cheaper components, and a couple other things that come together to make space more accessible to everyone on the planet. And this is really great commercially. I like to tell, I have to raise money from investors, and sometimes they get a little bit scared of, when I tell them I'm building space hardware, that sounds expensive and scary, and getting to space sounds very challenging. But I like to tell them that low Earth orbit is really just a different place to put your sensors. Just like putting them on a radio tower or laying cable under the ocean. It's just a different place to put modems and cameras. And so commercially, some of the applications that people are using small satellites today for include monitoring crop yields. They'll take pictures of crops and try to forecast the yields for that year, and they'll maybe sell that information to banks who can price futures based on that data. Companies that are sending big shipments across seas can track those ships almost in real time. We're not quite there yet, but hopefully soon. And then there are, some more kind of warm, fuzzy things happening with small satellites today that just weren't possible before. So this is an image of a wildfire burning. And so better predicting and responding and monitoring natural disasters is something people are starting to do with small satellites. And I had a favorite example that is a couple years old now, but there was a mobile breast cancer clinic that would drive around and do breast exams, and the doctors would put the results of the exams onto a USB drive, and then 90 days later, they would drop it off at the doctor's office. So I think it was the nurses on the van, and they would drop it off at the doctor's office every 90 days. But that can be a long time to wait for some, later stage cancer patients. So the mobile breast cancer clinic signed a contract with a satellite service provider, and they now upload the data in real time to doctors' offices. So those are just, a couple of very small examples of all the things people are starting to do with small satellites. But it's a very exciting time we're living in right now. So unfortunately, though, there's a problem. Started a company based on this, so of course there's a problem to address, right? Not everything from a large satellite scales down that easily to fit on a small satellite, and propulsion is one of those technologies that's hard to scale down. I think I have a slide on a little bit more detail on that, but as far as the technology. But without propulsion, small satellites are often launched into low orbits where there's a non-negligible amount of air particles still there, which impart some drag on the satellite and cause it to deorbit much more quickly than the designers and manufacturers would have hoped. So with propulsion, you can combat that drag force. Without propulsion, these satellites, you're often not really launched to exactly the orbit you would have liked or would require to perform your mission. So without propulsion, you can't correct for kind of offshooting your orbit or reaching your ideal final destination. You can't necessarily avoid collisions very effectively. As I'm sure a lot of you have heard, there's debris in space, and over a multi-year mission, it becomes important to have capabilities to avoid colliding with the debris, to turn your satellite into more debris. And then there are very exciting kind of interplanetary or other science missions that you just need propulsion to be able to perform. So there are a couple ways that folks achieve propulsion on a spacecraft. And they all come down to conservation of momentum. So matter coming out the back of the rocket makes the rocket or spacecraft go forward, as our friend here is finding out the hard way. Can I pause that? No, it's just going to keep playing. Okay, so typically people are more familiar with chemical rockets, Elon Musk and Falcon 9s and so on. So that's, okay, how do I make it stop? Okay, we'll be on this slide. So chemical propulsion, that's an example of it's combustion. So you have hot gases. Combustion occurs in the chamber, and you're expelling the products of combustion out the back. And that matter, mass times velocity out the back, that pushes the rocket in the opposite direction. The other main type of propulsion is electric propulsion. So instead of getting energy from combustion, the chemical energy, you're using energy from, it's electrical energy from solar panels or batteries. And you're still accelerating matter out the back of the spacecraft. You still need that momentum exchange to move the satellite forward. But the conversion to kinetic energy of the spacecraft comes from electrical energy acting on charged particles instead. So that's what we're going to focus on more today. So this is a conventional ion engine borrowed from space propulsion class at MIT. Okay, so I heard you guys are fine with getting technical during this thing. So let's see, what's going on here? So into this ionization chamber, a stream of neutral atoms like xenon or argon is injected. Also into this chamber, a stream of hot, high-energy electrons is injected. And the job of those electrons is to find a neutral atom, collide with it, and form an ion. Then some fraction of those ions that are created will find their way to this extraction and acceleration grid where there's an electric field applied, and that electric field will act on those now charged particles and accelerate them out the back of the spacecraft in this direction, pushing the satellite this way. Another thing to note is that those ions that came out of the back of this engine are all of a single polarity, and so you have this charged beam coming out the back. So that's bad news. If you have a charged beam, it often, if we just left it like that, it would come back and impinge on the spacecraft or other nearby spacecraft. So to remedy that, there's an external cathode that's also injecting electrons. These are much lower energy, but their job is to neutralize that beam so that it doesn't become attracted to anything else nearby. So that's how an ion engine works. So this is one type of electric propulsion that's been used on those really large satellites that I showed earlier. If you tried to scale down this ion engine, first looking at the actual hardware, you would first need to scale down this ionization chamber. And so that chamber would become smaller. You need to fit it on a small satellite. So you'd be injecting these neutral atoms into a now smaller chamber. You'd be injecting those same electrons into that chamber, but what you've done by shrinking the size of that is made it so that both of those particles leave the chamber faster. It's not as big. They're injected maybe with the same energies at the same mass flow rates, and they'll leave the chamber smaller before they've had a chance to meet and form an ion. And that is unfortunate. So to combat that, we can't make the chamber larger again because we're trying to fit it on a small satellite. You actually have to inject many more high-energy electrons, and that then becomes a very challenging thermal problem. You have a lot of thermal waste heat going to the walls. You may melt the material. The spacecraft may have a hard time of rejecting that waste heat, and so on. And so that's actually been a pretty significant hurdle for satellite designers trying to use existing electric propulsion systems and scale them down. And so in the Space Propulsion Lab here at MIT, that's what we were working on addressing. Is there a way to still leverage the benefits of electric propulsion, so using electrical energy to accelerate that matter out the back of the spacecraft, without running into this thermal challenge? And so what we work on is called an ionic liquid propulsion system. And you can tell by the name that instead of a neutral gas, we use a liquid propellant. And that liquid is conductive. It's just positive and negative ions. And we put that liquid into an ion emitter device made of several actual physical emitter structures that we'll get into in a minute, and then apply a potential between either that liquid or the emitter and a downstream extraction grid. So we also have an extraction grid just like a conventional ion engine. So this potential difference sets up an electric field, and our ionic liquid propellant is existing within that field, and it's conductive. So it actually feels a stress or a force due to that electric field. So let's say we keep increasing the potential that we're applying between that gap. The liquid feels a stronger and stronger force. It starts becoming deformed, and eventually, if you keep increasing the potential, the liquid will form a conical shape. And at the tip of that cone, since the surface is conductive, can someone tell me what the electric field might go to at the tip of that cone? So it's a very sharp point. We can think of it as did someone answer over there? Yeah, exactly. So as the radius of that cone becomes smaller and smaller, we're increasing the tip, we're approaching the tip of the cone. The electric field, as the radius approaches 0, the electric field would actually approach infinity. But that can't happen. We would create a wormhole or something. And so instead, a jet of charged particles actually issues from the tip of the cone and is emitted from the device. So you can fine-tune the parameters, the liquid conductivity and viscosity and the field you're applying and the surface tension. And you can design the system such that it emits pure ions from the tip in a sort of evaporation type process when the electric field is strong enough. And so that is modeled here by this equation. So this is the current density. And this basically represents ion evaporation from our conductive liquid here. The ions want to stay, they have some affinity towards one another. They want to stay in the liquid with their fellow ions. And so once you have to apply a high enough electric field to overcome that ion affinity, and then you can start evaporating ions from the surface. So through this ion emission mechanism, we're able to address, this occurs on a very small dimension. The ion emission site itself is on the order of 20 nanometers, and I forgot to look up like an analogous thing, maybe a human hair or something. Someone can chime in. It's a very small area, and what that means is that we can build ion emission devices or ion engines that are inherently very small, about the size of a human hair, though you would need some kind of packaging and all sorts of other things around that. But essentially, by using this liquid propellant and this ion emission technique, we've been able to overcome this fundamental scaling limit of more traditional electric propulsion systems. Yeah?
So for the liquid you're using, I think that not 100% of the mass will be shot out, right? Because the liquid itself, like, is liquid itself going to be shot out in terms of your ion, or is the liquid containing sort of ion particle, and the particle is being shot out? So you mentioned there will be like a sort of out of this beautiful liquid in here.
Yeah, that's a great question. So normally when people think of maybe a conductive liquid, you'd assume that there were some charged particles and they were dissolved in water or some other solvent. But in fact, in this case, the liquid itself is just positive and negative ions, and it's actually it's a type of salt. So it's like sodium chloride that just happens to be liquid over a very wide range of temperatures. So it's not actually dissolved in any. There's no water. So in fact, if you alternate the polarity, so if I only operated it in one polarity, I would only extract ions of one type. But if you alternate the polarity, you can extract ions of the other type, and emit almost all of the propellant in ion form. Yeah, it's a good question. So, I don't want to make it sound like it's been necessarily an easy journey, and many of you may recognize this situation. This is a poor fellow from the internet whose computer must have gotten wet, and he's attempting to use rice to absorb some of the water that's still in his computer. And going through a PhD on a device like this is kind of what I have burned into my memory, which is that working on small devices, remember I said human hair, and those voltages, high voltages across small gaps with a liquid equals, this situation a lot of times. And so we've had to work hard to figure out how to keep the liquid where we want it to be, to not start bridging the gaps between those electrodes and so on. But when it is working, it works very efficiently and very well. So here's a video of a conductive liquid being placed in an electric field, being stressed under that field, and then assuming a conical shape, and then you can actually see the jet spray there from the tip of the cone. I don't know, can I make it play again? Yeah, I should have looped it. But there you have it. So that's the main operating principle of the Ionic liquid electrospray system. So at Accion, we've taken this technology and we did a lot of this work in the lab as well. And this is ultimately what we're commercializing and trying to make available for all these folks launching small satellites. So this is the kind of crux of where all of the magic happens. This one's my hand, and that's one thruster chip. So if you were to look closely, you could see that on the surface of that chip, there are about 480 holes in that top grid, and that grid is silicon. That one's gold-coated silicon. So 480 holes, and each of those holes is centered over one of those emitter structures that I mentioned. And those emitter structures hold the liquid. They transport the liquid from the propellant reservoir to the tip of that structure, and then that top grid is grounded. We apply a high voltage to the liquid itself. That field is set up, stresses the liquid, and ions come out of that grid there in the direction out of the board. So the satellite would be accelerated in the opposite direction. Yeah?
You said high voltage.
Yeah. Anywhere from like 700 to 1500 volts. So not too high, I guess, but it's all relative. Our electrode separation is on the order of about 100, 150 microns. So that's quite a strong field. That potential over that separation is on the order of volts per nanometer, essentially. Yeah.
What are the specialized things like nanotechnology or quantum?
Yeah, so in our lab, I mean, we all had a background in aeroastro. A lot of the disciplines that we had to draw in are, mechanical engineering, electrical, a lot of microfluidics, which, when I'm hiring at Accion now, I'm looking for biotech type of people that have done microfluidics, like labs on a chip sort of backgrounds. So it's, fortunately it's interdisciplinary, so it's not boring and is always different. And those are the main fields we draw from. Yeah. So there are, depending on the material, there are many different processes for getting small holes. So each one is, I think right now about 400 microns in diameter, and we use, since it's a silicon chip, we use a process that's found in a silicon MEMS foundry, similar to those used to make computer chips, and it's a plasma etching process, DRIE, for those of you that know MEMS processes. Great, so where all the magic happens. And to turn this into an actual propulsion system, you may have guessed that this isn't everything that's required. This is just what we call the thruster head. So we'd use anywhere between 2 and 200 of these chips together to make a thruster head. Anyone pick up on why we might need, why I said 2 and not 1, even numbers? Yeah.
So you can balance the amount of thrust and spacecraft so it doesn't mix somewhere.
We do have to think about that, but that's not why the even numbers of chips. Yeah.
You only emit one polarity ion at a time. You want to neutralize whatever it's something so it doesn't trap the
Yeah. Yeah, that's right. So from that ion engine I showed before, there was an external cathode that was required to inject those electrons into the beam to neutralize it. So rather than needing one of those, we just have one chip emitting positive ions next to another chip emitting negative ions, and we don't need that external cathode anymore, which helps to save on part count and cost and complexity. Yeah.
For all the stuff required for the propulsion, how much is the weight? All this stuff, and then
Sure. So we have kind of a whole product line, but our first systems weigh around 1 kilogram. Yeah. G's like small or G's like big? Okay, yeah, right? So the thruster head, an even number of chips to make up the thruster head. Those, the things missing from this picture are the propellant supply system or the propellant reservoir. So those would be perhaps attached to the back of this chip or maybe located away from it and connected by some sort of feed system if the satellite manufacturer required that. And then we also need power electronics. So we have to take the power and command from the spacecraft, step up the voltage to the voltage we need, monitor the health of the device, and so on. And so the power electronics is the third component. And with those three, then you have a whole propulsion system. So just to reiterate, the two main differences between this and more conventional electric propulsion. The first is the propellant, and so this is one of the molecules of the propellant that we particularly like to use, or two of them. And so because we use a liquid propellant, we can make these devices inherently small, like I mentioned, but there are some other advantages that are unique to ionic liquids. And one of them is that they have a very negligible vapor pressure. They don't have zero vapor pressure, that's not possible, but at the temperatures and pressures that our systems experience in space, these liquids don't undergo any measurable evaporation. And that's very convenient when you're trying to build a system for a spacecraft if you don't have to store the propellant in a pressure vessel with all sorts of complicated pumps and valves. So that's a huge one from a safety perspective and a weight and volume perspective. Like we hit on already, no need for an external cathode because there are positive and negative ions in the liquid. And then the other one is, the other main difference is related to the manufacturing technique. So the propulsion systems of the past 50 years, typically the US has needed anywhere between 1 and 30 of them per year. And those are very small volumes. And so the systems were not designed to be produced in a cost-effective way. They're not batch manufacturable. They're kind of made like bespoke jewelry with a lot of trade secrets and inherent knowledge. And so we tried from the beginning to use processes that could be scalable to address a lot of the new applications coming online for small satellites. So we use mostly MEMS processes. We also use just CNC milling. Hopefully one day we can use 3D printing. We're still watching that to see when it becomes, when the resolutions become small enough for us. But this is one of the main differences for us as well. And perhaps what we think is most exciting is that the amount of thrust you can squeeze out of one of those chips for this technology essentially surpasses, theoretically, we'll see how it comes out, but any other type of electric propulsion known today. So how close you can put those emitters, ion emitters, to one another is limited by a couple things that we don't expect to hit for another couple hundred microns as far as how close we can move them together. And so that's what I'm showing here in this chart, and which is what makes us excited to bring this technology to market for those commercial missions I talked about, but also for some future interplanetary missions and science and exploration as well. Okay, so I remember sitting in your seats. It feels like not that long ago, but now seeing you guys, I think it was a long time ago. And thinking about, there are so many paths out there. I want to do a PhD, but maybe I want to work at a small commercial company. How do I reconcile these things? And really, I had no idea. And today, sometimes I still have no idea, but here we are. But we decided to take this technology and try to spin it out into a commercial company and manufacture the devices and sell them to the greater aerospace community. And that wasn't an easy decision. Some days I think maybe if we had turned the technology over to a company like Boeing or Lockheed, would it already be out there in the world? And this group of fine grad students here decided that, no, not necessarily. What we were doing had never been done before. Traditional companies weren't used to using ionic liquids. They weren't used to using MEMS techniques to build propulsion systems. We actually, I think somewhat reasonably concluded that it could take a big company like that actually longer to mobilize and spin up those resources to get a system like this out on the market. And so we formed Accion Systems. This is a placeholder name, Electrospray Propulsion Systems, LLC. Very creative. We formed this in 2012, and so we've been at it since then. Our first hardware was supposed to launch a couple weeks ago on one of those Irvine CubeSats that I mentioned on a Rocket Lab launch. That's currently delayed, but should be going up hopefully this week or next week. So that's Accion's first hardware. And in general, we're thrilled to go to work every day, hopefully pushing the space industry forward and doing what we'd be doing in our basement anyways, even if we weren't doing it at work. So that's everything. You can find our website. Thank you. Okay, and I have quite a bit of time for questions and discussion, and I saw one up there. Yeah.
So I have two questions.
Sure.
How much would one of those systems cost if you had like 4 chips? And second question is, how much power do they draw?
Sure. So can't tell you the cost, but I can tell you the ballpark. For 4 chips, it's less than 100K. We're in an expensive industry, guys. And the power draw for, again, 4 chips is less than probably 3 watts all in.
Okay.
Yeah. Mm-hmm.
So
extend a CubeSat's operation lifetime?
Sure. So the mission I have off the top of my head is for, I think it was 12 chips, but you'll have to bear with me on that one. So a system that fits reasonably within like a quarter or a third U of a CubeSat, and then we were looking at a mission for a 3U. So takes up about a third of a U in a 3U CubeSat. Launched to, I think I did, this was 400 kilometers. Without propulsion and solar mean and various other assumptions, that CubeSat would deorbit within like 7 months, and that system that I just spec'd could extend the lifetime to around 3 years. Okay, let's go over here. Yeah.
So what was the transition like from your
Yes.
school project until like a project? Like what was the process? Sorry.
Gosh, so there were a few lessons right off the bat, like doing a PhD, you know, you're trying to get something to work a handful of times and really interested in the science and how you might extend those conclusions into other applications and into the future. Doing it at a company, you need to really care about like the supply chain and is that vendor reliable, and do I have a statistically significant result for that my customers will believe. So it's very different things that you have to care about on the hardware side. Personally, it's a different, you know, work environment when you're doing graduate research. You know, you're focused on yourself. No one else is really paying, you're not under that much scrutiny all the time. Now I have a team of 31, and it's like I have 31 bosses. So for me, it's been quite a transition. Yeah. Yes.
So in terms of the technology being more accessible for everyone, obviously, like now that it's more accessible, more people will put their own CubeSats out there.
Mm-hmm.
How will sort of, I guess, traffic be managed, especially when more and more people start putting their own satellites into orbit?
Yeah, I mean, that's a great question and is like a very hot topic today in the space industry. So I don't have a great answer for you, but right now it's hardly managed at all. It's there's a guideline set forth by the UN, and they let each space agency kind of manage that within their country on their own. And so the guideline, then the rule that NASA then imposes in the US is that you have to deorbit your satellite, or it has to deorbit naturally within 25 years. So you either have to launch to a low enough orbit such that that will occur naturally, which is about 475 kilometers, 500, or you have to prove that you have propulsion on board that can deorbit it within that time frame. I think we're almost to the point where it's going to become very kind of dangerous and precarious to launch through some of these belts of debris. And it seems like no one's going to do anything until it actually becomes a real problem. And I would bet that at that point, you're going to have much more directed slots even within low Earth orbit, because right now it's a little bit like the Wild West. So I would recommend keeping an eye on that and seeing if there are ways to get involved, but I'm not sure where we'll end up. Yeah.
So it's like the ion liquid chip. It's sort of like a consumable, right?
Sure. Yeah.
Yeah. So how long would one chip last since it's like that?
Well, so there are a couple different life-limiting factors. So a conventional ion engine actually is the ions are always impinging on that grid, and so those fail when those ions etch away the grid to a certain degree. In theory, we locate our emitters right behind holes, and so we shouldn't have any sort of ion impingement. That's not true. So we do have some, but that probably won't be our main life-limiting mechanism. We would love to get to the point someday where it's just a matter of how much propellant we carry on board, and when that runs out, then lifetime's up. But today, after several hundreds of hours of operating, we do see liquid bridging gaps and shorting our electrodes. So that's kind of what our big technology push is right now. After 500 hours, how do we stop that from happening? Yeah, up there.
Where or how do you find investors that are specifically interested in investing in space programs?
Yeah, that's a great question. I mean, these are all great questions. But so when I first started fundraising in 2014, I did have to find investors that were very specific to space and space hardware. And so our lead investor at that point was Elon Musk's partner at PayPal, who Elon Musk left and started his companies. His partner left and started Founders Fund, and so that was our lead investor. So it was someone very specific, very familiar with space, part of that community already. Now, fast forward 4 years, and every large investor wants to invest in space, and they don't seem to be as afraid of hardware and space itself anymore. So it's become much more of the cool thing to do, I guess. Yeah.
How did the specific impulse and thrust to mass ratio of your system compare to more traditional arc on or xenon-based ion thrusters?
So specific impulse is about on par with a traditional ion engine and Hall thruster, same ballpark. And thrust, you said thrust to mass. So because of the lack of pressure vessels, a complex feed system, and we don't actually need a large ionization chamber, if I look at our most favorable case, we're about 13 times smaller in terms of mass and volume. Yeah.
Just out of curiosity, who would you say your largest clientele base is? NASA, defense industry, private corporations? Curious.
Yeah, so if you had asked me that a few years ago, I would have said it will definitely be other small startups that need to take advantage of radical new technologies to make their business cases close. That wasn't true at all. They're very risk averse. And so it's ended up being the bigger kind of incumbents like the aerospace prime contractors and DoD that have been more eager to adopt a new technology for the first time.
Thank you.
Yeah, yeah, white shirt.
At some point you create a solution to make these chips reusable and more cost-effective?
So I think it will still be limited by the amount of propellant we can carry on board, because otherwise we'd have to go retrieve the chips in order to reuse them. So it's, for us, a matter of extending the reliability and lifetime of the chips, and eventually it will just be a matter of how much propellant can our customers take on board. So there's not a lot of, we don't have as much control over the system as, Elon or at Blue Origin or anything. We can't re-land necessarily. Maybe someday as they're deorbiting and burning up, we can go retrieve the chips, but they're quite small, so it's interesting. Let's see, yeah.
So how much less expensive do you think a CubeSat would be compared to the $2 billion spaceship?
I know you can buy all of the bits for a 1U CubeSat for around $8,000. So it's obviously not doing the same exact mission as a $2 billion satellite, but to be on the order of single thousands of dollars is quite an incredible feat.
And do you propel it?
Yeah, on a 1U CubeSat, it's still kind of hard to fit any sort of propulsion system, but the propellant there is, a few dollars versus being tens of millions on the larger example.
That's cheap.
Yeah. Yeah.
Can you elaborate on the effect of microgravity?
Yeah, so as far as once the liquid is all the way at that thruster chip, capillarity and surface tension dominates compared to gravity, so it behaves very similar to how it does on the ground, since that's true on the ground. The point where we do have to worry about it is when we have kind of a bulk amount of propellant stored in the reservoir. And so in that case, when you're testing on the ground and you have the chip on top and the reservoir here, the liquid will preferentially be on the bottom, so you have to make sure you have a way to transport it from the bottom to the chip. So we, again, do that through capillarity through a wick system. When you're in microgravity, it could effectively look like the system's upside down or on its side. And so that same way we made sure the liquid would come out of the bottom won't necessarily help if all the liquid has chosen to be on the side of the device. And so in that case, it's kind of a game of making all the other surfaces non-wettable so that the liquid will still preferentially go to the places that we want it to. And it's actually, this is something that people have to deal with for all propellant tanks. There are all sorts of wetting materials that they use for vanes or sponges to trap the liquid in certain places and keep it out of others. So it's a game of wetting, non-wetting, basically. Yeah.
Affect the reaction, that ion reaction, at all, and also what fail-safes you took for your electronics on board from radiation?
Sure. Yeah. So the propellant that we use has undergone some testing, not by us, but by some other folks, and we've looked at the results of that. The liquid seems pretty stable and non-reactive to any radiation environment up to, I think it was 10 kilorad. And so that is as far as we've tested that so far. For the electronics, we do a combination of shielding and buying higher radiation tolerant parts. So for some of our customers, we even have to do some military grade components that either have a lot of redundancy within each chip or come with additional shielding as well. And then fortunately, our electronics are also within the spacecraft, so we get to benefit from other structures around as well. But yeah, it's a real concern, especially for longer missions. Yeah. Yes, good. All sorts. So I guess there are a few ways you could tackle the problem. You could say, well, is the liquid always going to show up there? Should we figure out a way to clean it? Or there's an option of, let's say we expect a short. Can we just burn off the short and make the liquid evaporate at a certain temperature or something? Or you could look at how do we seal it more effectively so that it never happens in the first place. And we're basically trying all of those things all at the same time. So check back soon and I'll let you know. Yeah?
Do you have any patents on the design of the chip?
Yeah, so through the work at MIT, there had been patents starting in the early 2000s, I believe, maybe late 90s, and then we've continued working together, so there have been follow-ons and probably many more to come. Yeah.
Do these infringements come by the chip, from the chip itself, or is it like after shake testing, like right up space isn't necessarily a smooth one? Is it like after that shaking that these chips start having these infringements and short?
Yeah, so we had seen both in the past. So the environment that the device sees during actually even storage is important, and launch, and then in space, those are all considerations. And while it is nice to have a completely passive system that's open to vacuum, it also means that compared to a traditional system where the propellant is sealed off and it doesn't really see this depressurization and launch at the same time, our liquid does see that. It undergoes this pressure drop while it's vibrating through launch. And so that's been something unique to this system that other people haven't had to deal with. And we did see some leaks from that early on. But the challenge we're trying to address now is related to after many hours of operation. Yeah. Sure. That's okay, I'll get him after you.
Who are your customers?
So right now, mostly the DoD and Boeing and Lockheed type of folks. Hopefully, and actually, like I mentioned, Irvine High School. So some people doing technology demonstrations or science missions, and eventually some of the smaller commercial companies that you may have heard of, like Planet Labs and some Inspire and folks like that.
So can I call it now?
Yeah, sure.
We want to thank Natalia here. We have the BeaverWorks T-shirt, and would you like to come down and help present? While we're standing here too, I also want to point out we have 2 groups from Mexico also here this week. You guys want to wave? They are participating in the race car, and so we're hoping that we've got a little international collaboration going on today too, or this for the next 2 weeks. Thanks for coming, guys.
All right, guys, I need CubeSat and Medlytics just to stay here for a second, but that doesn't mean everybody gets